and produced by the Sound of Knowledge Incorporated.
Thompson. I work for Argus Systems Group, and I'm a director for the company, but my title is Software Evangelist and Visionary, which essentially means I get to jump up and down and wave my arms around a lot and act like I know what I'm talking about. So I'm going to do a little bit of that here today. Now, the talk I'm going to be giving is going to be on securing network systems, on public networks, and it applies largely to private networks as well. But that's really what I want to focus on. It's going to be a technical discussion, and in regards to platform security as opposed to application level security. So I'm not really going to be talking about things like SSHD and stuff like that, but rather the kernel and operating system level security. I will be using a product that my company makes called Pitbull.compact, which is a trusted operating system product, as a reference to allow me to actually give this talk. However, most of the concepts that I'll be talking about apply directly to other trusted operating systems that are available today. Just to tell you a little bit about Argus Systems Group, we are in fact a operating system security provider. All our work is in the kernel and at the operating system level. And we create a commercial trusted operating system called Pitbull, which I just mentioned a minute ago. There's really 4 parts that I'll be discussing here in my talk today. The first is going to be just an overview and a brief discussion on standard operating systems and standard platforms, and what the failures are of the security architectures that are implemented in these platforms. Once I go through that, I'm going to get to probably what will be a little bit of a drier piece of the talk, but I hope you'll bear with me, which is going to be going through and talking specifically about the features and functionalities in trusted operating systems. And I'll go into a little bit of detail so that all of you will have a fairly strong understanding of what those mechanisms are, as opposed to just drawing a few rectangles and squares on a screen and saying this is what it is. So I want to give you a little bit of understanding. And what that'll lead me to really is to the next piece, which is to discuss how trusted operating systems actually solve and fix many of the failures of standard operating systems and give you an understanding of why that is. And then finally, to actually apply this technology and these features to real architectures, how you can actually use this stuff and make some meaning out of it instead of just talking about it theoretically. I'm going to start off with a quote from the NSA, and everybody at my company loves this because it boosts what we do, obviously. The quote is simply that the threats posed by the modern computing environment cannot be addressed without secure operating systems. Any security effort which ignores this fact can only result in a fortress built upon sand. The problem today is that we're building our architectures and we're really focusing on 2 things. One is application level security. We're trying to do everything we can do to secure the application. The reason for this is if you ask anybody who's a halfway decent hacker or somebody who does any kind of intrusion, once you break into a system, first you're coming outside, you're coming in remotely, and you break into a service, and you have an account, even if it's not root, the game's still pretty much over. Because it's really then only a matter of time before you find an exploit or you find a problem on the system that allows you to gain root. And the reason is simply that today's platforms, and though we kind of take it for granted and deal with the fact, but today's platforms cannot protect themselves against attack, and they're not, and we see it every single day. So let's talk about the SAND, which is standard platforms. There's really 3 basic areas worth mentioning here. 2 are actually problems, and the other, discretionary access control, is kind of derived with how superuser and root ideas are dealt with. So, superuser root. On a system, there's a concept of privileged access, and on standard Unix and even on Windows NT, you pretty much either have privileged access to a system or you have no special access. You're just a regular user. So under Unix, if you need to mount a system, you become root. If you need to bind to a privileged port, you become root. If you need to do anything out of the ordinary, you become root. Except when you become root, you have access to everything. So you have privileged access is either on or off in this case. Also, under standard Unix, there's only one user who's considered to have the special access. We call it root, but it's really just UID 0. And we can create lots of other account names that are called that. And what this does is it creates a simple, well-defined common point of attack on a standard platform to go after. So all you have to do is go through and find all your set UID programs or any program running as root, break it, and you have access to the entire system. Or you can go after kernel bugs. Those are a little bit harder, but can still exist as well. the ramifications of this and what people will go after when they're trying to make these kinds of attacks. There's really, there's two problems, and there's one other thing that's worth mentioning. And the first, of course, is buffer overflow attacks, which I'm sure everybody here is at least passingly familiar with. The second is the idea of taking existing root programs, or even daemons if you can, and misdirect them, get them to do something that the programmers never intended those programs to do. And finally, on standard Unix systems, if you become root, you have access. One, root owns just about every file in the system, except for the few things that you create for users. And then the root also gets the bonus of overriding all security checks on a system and can then, therefore, go and access all files. Just to briefly mention about buffer overflow attacks. A buffer overflow attack is essentially an attack where I'll just use the word hacker, and people can get upset about that if they want to, where they take programmatic code and insert it into an existing program that's running. And the idea is to try and get this code to actually run in that process. And this is done fairly simply. I'll give a brief description. The idea is that a program will have some function that's executing, and inside that function there'll be a buffer. And if an attacker can then go and overwrite that buffer to putting code into it, but beyond even that buffer's length, then what you do is you wind up getting into a situation where you're overriding that memory in the stack, which is where function variables and buffers are stored. And then you can go and write down to another special place, which is called it's essentially the return function pointer. What happens then is when this function exits, when it's done, and it needs to go back to the calling function, then the CPU will then look at this stack, or actually the code will tell it to, and then it will jump to the original code. Well, if you've modified that pointer, you can then tell it to jump to a new piece of code. Well, this is the code that you've just inserted into the buffer, and now all of a sudden you have a program which is running as UID 0 or some other user executing code for you. You can get it to do it pretty much whatever you want it to do, depending on how good a programmer you are. And so attackers will use these kind of mechanisms to typically go after set UID programs and daemons running as root, because once they get it, it's over once you have root. But they can go after other daemons that are running as other users. For example, if they don't have local access to the system yet, to get a leverage point onto the system, to get a user account, and then use that to launch off and attack the system some other way. And if you're at all interested in buffer overflow attacks, I recommend attending Greg Hoagland's talk, which is at 4:30 today. And he'll be talking about this in much greater detail, and probably with more slides. The next kind of attack that people will go through is the idea of misdirecting root programs. And this is simply taking an existing program and trying to trick it into performing an action that the programmer never thought that this program would do, never considered it. Or if they did consider it, they made a mistake and didn't fix it. And there's really three ways that people go about doing this. The first, and probably the most common, is race conditions. And the idea behind this is that, for example, you might have a program that needs to create a file, for example, in /temp, that it's going to use for some data. Well, the first thing it might do is check to see if that file exists already. And then if it doesn't exist, it knows that it can create and use it. Well, there's a lag time between when you check to see if the file's there and when you actually create it. And somebody who's clever can actually try and create that file in between the time that the check is made to see if it exists, and between that time and the time that it actually creates the file. Now you can do some clever things. For example, you can create a link. You can make that file a link to another file, like say Etsy Shadow or some other file in the system that you'd like to change or modify. Well, this program, since it's running in its root, can pretty much do anything it wants to that file. You might be able to get it to overwrite the file, to create it new with different permission bits. You might get it to insert data into the file. Lots of different things that you can do to actually gain root access to the system and then take control of the box. The next thing that people will try and do is that if you have a set UID program or any program running as root, it has access to every file in the system. Well, if you have a set UID program that takes in, for example, a configuration file, you might be able to pass in and tell it, look at this file to figure out how you should operate. Well, if you can tell it, hey, look at Etsy Shadow to do your configuration file, then the program's going to read that in. Chances are Etsy Shadow is not a valid configuration file for many programs. So what happens is, of course, that many well-written programs will actually return debugging information. They'll tell you, hey, your configuration file's broken. It doesn't look right. Here's what it looks like. Now all of a sudden you see Etsy Shadow, and you probably have the root password encrypted, but chances are you'll probably be able to break it with enough time. And then the last attack is, I haven't seen this one personally, but I know that it exists, is if you can tell a program, for example, where to create a log file or where to create a temporary file, where it should create its temp files at, then you can pretty much do the same thing that you did with a race condition, except you don't have to try and beat the race. You just can simply tell it, hey, look at this file, and override it and try and insert information into the file. Or you can use it to create files in a directory that you might not normally be able to, for example, /lib. Wouldn't it be great if you could insert your own libraries into there and get people to use those? Next thing to talk about is discretionary access control. This is a really big word for something you probably all know as is permission bits. We have user, world, and group writable, readable, that sort of thing. Discretionary access control, or DAC, or I should say it's also access control lists are the same thing. Just want to make a few points about DAC because this will become a little more meaningful when I describe another mechanism that trusted operating systems use. The idea here is that if a user creates a file under discretionary access control, that file is owned by them, and that user can choose whatever type of security they would like to put on that file. It's up to them. The next thing is that any user who has read access to a file has the ability to copy that file and give away access to that file to anybody on the system that he wants to. There's no way to prevent a user from giving away access. Same thing with write. All a user has to do who has write access is to create a setuid shell that set UIDs to that user's UID, and another user can run that shell, become that user, and have write access to the system. So there's no way to prevent this migration of data. You can't really protect your data on a system and decide who can see it and who cannot. The other thing to point out here is that a user, irregardless of the permissions on a file, even if you set them to 000, no access, can modify the file, because that user can go back and modify the permissions on the file again so that he can access it. And while this might seem kind of obvious, and well, why shouldn't he be able to do that? The point I want to make is that there may be times where you would have a user who, under certain circumstances, you would want to allow them to access a file. And under other circumstances, you would not. For example, an administrator. If your administrator is coming from your internal network and connecting to your system to, for example, add users, you probably want to let him have access to Etsy Shadow. However, if that same administrator is connecting from some public internet site, like from AOL or wherever, you probably don't want him to have access to your Etsy Shadow file, because in fact, it's probably not your administrator. And I'll talk a little bit more about how you can deal with those issues later. The other thing, again, to kind of bang into here is root is a common point of attack. On DAC goes into this mechanism as well, because if you become root, you override all of the DAC protections. All right, this is kind of the one that if anybody here has thought about this before, then great, bravo, but I suspect that most people probably have not. Under standard platforms, networking is actually not tied to operating system level security. We have network filtering, and we have the idea of we can restrict access to services. And we do this with firewalls, or you can even do it a little bit differently with something like TCP wrappers. And what we do is we say, if you're coming from this host, you can connect to this service, and if you're coming from this other host, you can't. But once somebody connects into a service or connects into your box, there's no way that you can further limit what their access is on your system. Their access will simply be the user that they come in at, no matter where they come from. They'll have that access. And the firewall doesn't protect the system anymore, because they punched a hole through the box, and now they can attack the system and access files in any way they would like to try to. And again, kind of pointing out the thing with networking is that a user connecting over the internet, over a VPN, connecting over SSHD, connecting over an internal network, all have the same exact access on your system. So to kind of sum up some of these core what I would call failures, because I know that there's a solution for them, is that one is that many services are running as root, many programs are setuid root, and they create an excellent point of attack that people go after, and in fact every day people do, and they're very successful at it. The other thing is that we have no way of saying that the same user, an administrator coming in from an internal host and coming in from an external host, has different types of access. If somebody gets the administrator's password and is able to either SSH in or telnet in remotely, they can come in as that administrator and they can modify your box. If that user breaks into another service on your machine and then SUs to that account, they can have the same access that administrator has. And right now, under standard platforms, there's no way to protect against that. So I would say with this that really on a box you get into a situation where compromise really only becomes a matter of time, because your security is only as good as your patch level. How many patches have you applied to your system? Are you absolutely certain that no exploits are on your system? Well, chances are there probably are. And so you're just playing this waiting game, and we're installing our IDS systems and hoping that we'll see that something happens so that we can deal with it. But it's all a catch-up game, and it doesn't have to be that way. So, the old paradigm becoming a new paradigm, trusted operating systems. I'm not going to go into the history of trusted operating systems or make a big deal about why they're so great, but rather I'm going to talk about their features, and hopefully you'll all come to the same conclusion. The mechanisms I'm going to be talking about are least privilege, or something you may know of as capabilities, which is POSIX capabilities, which are implemented or starting to be implemented under Linux. Authorizations, mandatory access control, and then the idea of actually applying security checks to network data into the network level. And then also talk about two application-level programs, which would be a security gate and CGI Daemon, which kind of come out as extensions of what we can do with trusted operating systems. And they'll make sense when I get through this to talk about that. To talk about privileges, just give some brief definitions, and then actually talk about how they're applied to processes and file systems and how they work. And then, more importantly, how privileges will actually move around a system and how they actually operate. There's two definitions worth understanding. The first is least privilege, and this is simply the idea that you take previously what you had is the idea of root. Root can do everything, UID 0 can do everything, and say, what are all of these things that root can do? Right? Take that and break it up into each of those little concepts. Root can mount a file system. Root can override DAC checks on read DAC checks. All these kinds of things. Root can shut down the system. Root can halt the system. Break those up into individual tasks, and then apply these privileges to programs or to processes and say, this is specifically what this program can do. To give an example, a web server. Web servers start off running as root if they want to bind to port 80. Port 80 is a privileged port, so it has to run as root. Well, there's really no reason that the web server needs complete access to your entire system, even if for a brief moment. So now with privileges, instead of giving it all of that access, you can simply give it a privilege which says, go ahead and bind to a privileged port. That's all you get. And then when it's done with that, it can throw away the privilege, and I'll explain that mechanism. The next thing is the idea of privilege bracketing, and this is kind of what I was just getting at. Privilege bracketing is the idea that a program will have a set of privileges or special operations that it can take. And it can take those operations, but when it doesn't need them anymore, it should get rid of the privileges. If it doesn't need to bind to a privileged port anymore, it can drop it. That way, if someone comes in later and breaks into the process, breaks into the web server or the CGI programs, then they won't have access to that ability because it's not there anymore. And so now you can actually design your software in such a way that there will be critical pieces of code that will operate in a privileged fashion that you need to check very carefully because they're doing something very important. But you can know for certain that the rest of your code will not be running in a privileged mode, and therefore only have the access of that user on the system and nothing else. So, I kind of harped on this before. Traditional Unix has one privilege, root. You're either root or you're not. You have access to everything or you don't. Under a privileging system, you break it up into different concepts. So you have things like a privilege for file system mounting. You have a privilege for read DAC, for overriding DAC read checks. And then you create some new privileges for trusted operating system concepts, like, overriding MAC write, or being able to give privileges to a process. So how do privileges work on processes? There's three sets of privileges that you can put on, that can be put onto a process, and in fact are put onto every process. And these are your limiting, maximum, and effective set. A limiting set is the maximum set of privileges that a process or any of its children can ever have during their lifetime. And so what this means is that if this process runs another program that would give it privileges that are not in its limiting privilege set, it can't get them. So you can very easily create a process, for example, a user shell, and say, this user can never have privileges on this system. No matter what they do, no matter what program they run, they won't be allowed to have them. And you can do that with a limiting privilege set. The maximum privilege set is simply the set of privileges that a program can use. And the effective privilege set is the set of privileges that it's actually using at the time. So when it's not using them, it can remove them from effective privilege set. And when it absolutely doesn't ever want to have them again, it can remove them from the maximum set. So to kind of describe the rules of how these things work, and a lot of this is going to be really common sense, so I'll fly through this, is that a process, as I said, a process can manipulate its effective privilege set. It can decide what privileges it's going to be using within the bounds of its maximum set. And and this set that it's using can never exceed what's in the maximum. And then again, the process's maximum set can never be greater than what's in its least privileged set. The other thing a process can do is it can always lower its effective set. It can drop its privileges. It can always lower its maximum set. If it has a special privilege, and you're going to hear the word privilege, privilege, privilege a lot. If it has the right privilege, then it can actually raise its maximum privilege set. So as you can guess, probably almost no program and no process on a system would ever have this privilege because it's very powerful. But you might put it on certain administrative programs. The other thing that you can do is that a process can actually lower its limiting privilege set. However, there is no way for any process, no matter what it has, to actually raise its limiting privilege set. Even if it has every privilege on the system, it can't raise it because there is no privilege that allows an override for this. So once you strip away your limiting privilege set, that's it. You have no access to special rights on a system. Privileges on file systems. Privileges are stored on every inode on the file system. So you have a case where every object on the file system can have privileges associated with it. So there's not this separate database that keeps track of things that you can try and trick. It's actually stored with every file. And there are 3 privilege sets that are stored with this, and they're the innate, proxy, and authorized privileges. Just to briefly describe these. Innate privileges are privileges that you put on a program and you say, when this program is run, it's going to have these privileges. So for example, the mount, I was going to say function. The mount program would have an innate privilege on it which says you can mount, right? Proxy privileges are privileges that a program will get if the process that runs it has those privileges already. So the privileges just travel along through proxy. And authorized privileges are a little bit special in that they are privileges that a process will get if it's run by a user who has a certain authorization. And I'll describe what authorizations are in a minute, and that will make sense. Privileges move around in the system in a little bit different way than they do under standard Unix. One is that if you fork, if you create a new process, the new process will have exactly the same privileges that the previous one did. Also, if you do a set UID, the program will retain its privileges. So changing user doesn't change your privileges. Under standard Unix, it does, because if you become something else besides root, you don't have special access anymore. So that's a little bit different. The other thing to mention is that when you do an exec, which is essentially running a program, that's when you perform all the rules that I just mentioned to decide what this new program that's going to be running will have as far as privileges. All right, to talk about authorizations. The first thing is to show kind of a distinction between privileges and authorizations, because sometimes this confuses people. Privileges are attributes which are actually placed on processes. Every process, every file, every object has a privilege set associated with it. And these privileges allow these objects or processes to perform specific security relevant functions in the kernel, like running certain system calls or accessing certain files that they may not necessarily have be able to pass an access control check for. Authorizations are not an attribute of a process, but rather an attribute of a user ID. So in this case, what you can do is say if a process is running as this user ID, then it will have a certain set of authorizations. And I'll explain what kinds of authorizations you might think about using. So user accounts will have authorizations. They don't have privileges associated with them. And authorizations are the way that you are allowed to run programs that have privileges on them. You use authorizations to restrict access to administrative commands or to programs that you only want to let certain people use. So when a user runs a program that's privileged, then what can happen is the program can go and look and say, is the user who's running me, does that user have this authorization that I require to run? If it doesn't, I can stop running, or I can run with a reduced set of functionality, or I can return an error. I can react to it in any way that I think makes sense. I can drop off my privileges if that person's not authorized. So I can throw away all my special access if I don't want them to have it. Also, as I mentioned, an executable can have a set of privileges on it which are called authorized privileges. And there's another thing that you can put on the file which is called privilege authorization, so it's kind of the two words flipped. And the idea here is that you can say on this program, if a user runs you and the user has this authorization, then put the privileges that are in the authorization privilege set into the maximum set of the process. And this takes place in the kernel as opposed to the user level. So there's no way for a user to try and circumvent this concept, I guess. The next thing to say is the other thing that you can put on a program is the idea of an access authorization. And you can say that a security administrator is the only person who can run this program. No one else can. And that will be checked as well when you do an exec call. When you try and execute the program, it will look at that file and say, it says ISSO, the security administrator, is the only person who can run this. And it'll fail the exec call, even though that user might have DAC access, might have Mac access, or any other kind of access that they need in order to run the program. So to kind of briefly mention what kinds of things you use authorizations for, we created a concept which is called roles, and it's the idea that certain users perform certain types of functions on your system. And 3 common roles, and this comes out of the government, you could name them anything you want to, is that you could have an ISSO role, which is essentially your security officer, the person who's responsible for security on the system. System administrator, the person who creates accounts on your system, but they may not necessarily need to set security settings on your system. And a system operator might be a lonely guy who just gets to shut down and reboot the system, and that's his only job. And what we do then is with these roles, we associate authorizations with them, and we would say that the SO has the ability to boot the system and the ability to shut down the system, and he'll have those authorizations. And then we can rearrange what authorizations users get depending on how we want to set up the system and how you want management of the system to actually take place. The next and extremely important thing to talk about is the idea of mandatory access control. MAC is an additional access control system put onto trusted operating systems. It's in addition to discretionary access control. So when you're accessing an object or a file, you have to pass a MAC check and you have to pass a DAC check. And MAC behaves very differently from how discretionary access control works. And in the government sense, and since this is how we implement it, I'll talk about it in this way, which is a model called the Bell-LaPadula model, if anybody's heard of it. The idea is that you take an object and you put a sensitivity on it. You say this object is protected at some level. And then you give processes a clearance. You say this process is allowed to access certain types of information, right? And these checks have nothing to do with user ID, only to do with security levels. And I'll show how the security levels are constructed to show you what that means. This will kind of summarize some of the differences between MAC and DAC. With MAC, the owner of a file cannot change the MAC setting on a file. If he creates a file, the file will be created at whatever level he's at. There's no way for the user to change this. So what you can do is you can lock a user into a level and say that whatever you do will be at this level, and there's no way for you to escape it. The next thing is that because the user's locked into this level, he can't give any information away. He can't copy a file that he has access to and give it to somebody else. Because when he copies it, it's going to be created at the level that he's at, which means it's going to be protected at least as well as the file was because he had to have access to the file. And kind of again paralleling the privilege discussion that I just gave, I'll talk about definitions, how these actually work, what sensitivity labels, or what I was saying was security levels, what they are, how they're constructed, and what they mean. Then talk about how they're applied to processes, objects, and also important ideas, how we actually use these at login, how we assign levels to users, and how that works. SL has 2 components to it. The first is called a classification, or class for short. And typically these are words that you probably have all heard at some point, things like unclassified, secret, top secret, or in the commercial world, public or confidential, things like that. And there's also another piece which is a non-hierarchical component, which are called compartments or categories, depending on what part of the world you're in or where you work. And these are things like, it could be a financial group or compartment, it could be your cryptography group, or it could be really boring names like Project A and Project B, whatever you want it to be. And when people write out a sensitivity label, they write the classification first, followed by a list of compartments. And according to this slide, people actually put a colon in between those two, but I can be honest, I've never ever written a sensitivity label that way in the 5 years that I've been working with them, but apparently the person who makes this slide does. So classifications work essentially like numbers. They're comparative. So a class can be greater than, equal to, or less than another classification. So top secret is greater than secret, secret's greater than confidential, and so on. And compartments work a little bit differently. Compartments are sets. So you have a set of compartments. And these sets can be subsets of other sets, supersets, or equal to the other sets. Or they can be entirely disjoint. And those relationships, I'll explain in a second how they work. or what they actually mean for an SL. And this is the concept of domination. If you talk about trusted operating systems, you'll hear the word dominate a lot, just as much as you hear privileges. And how domination works is simply that you say one label, label 1, is said to dominate another label, label 2, if the following two things are true. One is that your classification has to be greater than or equal to the classification of the other label in order to dominate it. So a top secret class dominates a secret classification. The second thing that has to be true is that the compartments of the first label have to be equal to or be a superset of the set of compartments in the other label. And there's a few brief examples up here. So for example, TSAB dominates TSB, dominates secret. I think the relationships are, it's fairly simple. It's just some set theory. And this is just a little diagram to illustrate how, if it's higher up, it dominates the ones below. And it's just really to illustrate the concepts that I was talking about, and I don't really need to talk about that too much. And obviously, the relationships could be much more complex than what's being shown up there. So, how do sensitivity labels work? Every process and file on a system has a sensitivity label. And when a process creates a file, the file is created with that sensitivity label every time. There's no way around that. And the other thing to point out is that when a system boots, the first process that's created has to be given some sensitivity label, the level that it's operating at. And because every process that it creates is going to get a sensitivity label exactly the same as what it has, you wind up with a situation where every process has the same level. That's what you call a single level system. So every MAC check is going to work. And so what you do is instead that during the log, you give privileges to certain processes like login, which will allow you to change the sensitivity label. And I'll go into that into detail, but that's what allows you to say that this user came in and now he can operate at a different level on the system. Now, how does all this work? How does mandatory access control do things with these concepts of domination? First is that a process cannot open a file for read unless the SL of the process dominates the SL of the file, which is all the little domination rules that I explained before. And a process cannot open a file for write unless the SL of the process equals the SL of the file. The other thing is, of course, that the SLs cannot be modified by the user, by the process, unless the process has privileges which allows him to do that. And all of these kinds of rules combined is exactly what mandatory access control is. That's what MAC is. So now we get into a situation where a user can copy a file and not give it away, and we can lock a user into a specific compartment or realm of operation that they can't escape from. And that has huge implications that I'll get into in the last half of my presentation. Processes have two extra SLs on them besides their what we would call their effective SL, which is the level that they're running at. And these are its minimum and maximum clearances. And minimum and maximum clearances say if a process has a privilege that allows it to change the level that it's operating at, that change has to be within the range of this maximum and minimum. It's the only way you can do it. On directories, we have the concept of a maximum SL added. And how this works is that files will have only one SL because a file is a single level container. You're saying it's rated at this level, and all the information that you put in it is going to be protected at exactly the same level. In a directory, you can have lots of different kinds of information. You have multiple files, and those files might be at different levels. And that's why you have a maximum and a minimum SL on a directory, because you're saying this is the range of data that I will allow to be placed into a directory. All right, to briefly summarize, a label dominates another label if the hierarchical component is greater and if its compartment set is a superset or equal to the set of the other label. And the other thing is that information can flow between two objects if the destination label dominates the source sensitivity label, which means that if I have a process that's trying to talk to another process, right, and this process is at secret and this one is at top secret, this process, the secret process, can write data to the top secret process because the top secret process is clear to see that data. However, when the other process at top secret tries to send information back to the secret process, it's going to fail because if you're secret, you certainly can't see top secret information. And so in order to have bidirectional flow, a complete communication channel, then you have to have a situation where both objects or both processes are at the same level. That's the only way that you can have it, unless you have privilege. Actually, I'm going to just skip these few because I think I covered everything there. Login label, this is the last thing with SLs that's important to talk about. Typically what you'll see on trusted operating systems is there'll be a database on the system which stores the clearances of users. And what you're going to specify in this database is the minimum clearance that the user can have, the maximum level that they can have, the maximum clearance, and what their label will be when they log onto the system, their default. And on our system, you can allow them to, if they come in through login, to say, I would like to actually operate at this level during this session. This is the compartment that I want to be locked into. So if you want to create a user who will only exist on a system at one level, then you make their minimum, their maximum, and their default all the same. And then they can only operate in that one realm of operation, completely locked into it. Now, the thing that has really big ramifications is network labeling. This is extremely important. It leverages all of the other things that I just talked about. The idea here is that we can look at network data and we can label the data based on rules, on a set of rules, similar to firewall rules, where we can say, if data comes in on this interface, if data comes in from this host, on this port, using this protocol, we're going to protect this information at a certain level. And because of that, where that data can go and how connections can be made can be restricted. And I'll explain some examples of that. And the other thing we can do then is we can say that a process on a system can't talk to external hosts unless the data that from the other host is going to be dominated by this process. Okay, I'm going to show a rule, a network rule, because this is the best way to explain how all of this works. And this is an example of a host rule, but it's a simplified version. I've actually pulled out a few things, and I'd like to just briefly touch on this. The presentation that I'm trying to give here is geared toward from the idea of protecting a server from attack. And you'll see how all this fits together at the end. It all kind of culminates in something pretty neat. There's a concept that's typically built into other trusted operating systems, and is in fact in ours, but I don't think it's very relevant here, is the idea of network labeling across the network. And the idea here is that if you have two trusted operating systems and you have a process on one talking to a process on another system, it can send a label across the network and it can say, this is what level I'm at. I'm going to explain something that will show you why this is very, very dangerous. There's an old program, and maybe some people here know about it. It's something called RexD. It's still around, and it used to be installed by default on AIX, not to pick on AIX. RexD is an interesting little program. It stands for Remote Execution Daemon. And the idea is that you can get it to execute commands for you on the other system. You can get it to do things for you. Well, the security model is what really becomes interesting. The client side actually tells the server side what type of access it would like to have on the system. There's no password, there's no security there. It simply says, I would like you to execute this program on that system as bin. Okay? Now you have a shell on a system simply by telling it that you want it. That's at bin. Obviously extremely dangerous unless you trust everybody who's going to be talking to each other. Well, on a public network, you can't trust that sort of thing. And it's the same thing with trying to send these ideas of labels across the network. So instead, what I want to talk about here is how we look at information that comes in off the network and how we can protect it and isolate it onto a system. And that's how these rules will be set up. The first part of a rule is simply saying, on a host rule, is saying, what's the host? What host are we applying this rule to? And the next thing is a net mask. In this case, it's 255.255.255.0. So we're actually looking at a subnet here. So the 192.0.0.14 could just as easily have been 192.0.0. It's going to apply to a whole network, this set of rules. The next thing we're saying is that this rule will apply to all incoming traffic and all outgoing traffic. So this is a bidirectional rule. And we're going to apply this to TCP connections, not to UDP or some of the other protocols. Finally, we're giving a range of ports that we want to apply this rule to. So this was actually selected to be to 21 through 24. So this is covering FDP, Telnet-D, and the mysterious port 24 that isn't really used for anything. But the person who created this slide decided to do that. Up until now, that rule is very, very similar to what you would see in a firewall rule. You're just specifying a network connection. That's all you're trying to state there. Once you have that, now you can actually apply some security to it. And the first part of a rule is saying the minimum and maximum level of information that can flow out of this connection. So if somebody's trying to connect to 192.0.0.14, they have to be somewhere between implementation low and top secret all. Well, that on a standard install system, that means everything. That's the lowest level and the highest level. But you could limit it to be more restrictive. And the next piece, which is actually the really interesting piece, is the default SL. And what this is saying that all information that comes in that matches this rule will be protected at this level, at confidential A in this case. Now, what does this all mean? This is where you can actually see some of the ramifications of this. I have a system here which is running 3 network interfaces. There's a public interface, a virtual private network interface, and an internal interface, which is the one pointing towards host B. I have 2 services running on the system which I'm interested in. One is a web server, and the other is an SQL server. The web server is running at confidential HTTPD, and the SQL server is running at confidential SQL. And you'll notice one of the things here right away is that the 2 SLs of these processes are disjoint. This means that these 2, what I would call subsystems, can't communicate with each other because they're at disjoint SLs, so they're totally separated. Now, what I've done is I've created a port, what I call a port rule here. At port 80, I'm saying that all connections come in at confidential HTTPD. And then I created an interface default rule, which means all other connections that come in over this interface are at confidential default. So now I have a situation where I can say where host A comes into the system and wants to connect to the web server. Well, he's going to be able to because the web server can communicate with his rule. And so he'll be able to talk to that. Now that same host trying to communicate with the SQL server won't be able to because he'll come in as confidential default to that process. And the SQL server will not be able to talk to him because his label is disjoint from that. And the same thing now, I extend that out to the VPN. I can see on this interface, host C can connect if he comes in from over a VPN. And on the internal interface, I can say host B can connect over port 80 and to the SQL server because I trust my internal interface or my internal users to be able to use the SQL server. Now, so that description right there really isn't a whole lot different than firewalls because you can just say, this host can access this service, this host can access that service. There's one very big difference here. If host A comes in and connects to the web server and breaks into the web server, breaks one of the CGI programs, he is going to be at con HTTPD because any process that he spawns is going to be at that level, which means he cannot communicate in any way with the SQL server. No matter what user he becomes, no matter what he does, he will be locked in at this level, and the rest of the system will be inaccessible to him. So what you do is you're taking this subsystem and you're compartmentalizing it. You're putting it into one little world so that even if somebody breaks out in that compartment, out of the application that's running in there, there's nowhere for them to go. All they have access to is that. And then later I'll talk about actually how you would secure a specific subsystem and the kinds of things that you can do to it to try and protect it. There's another interesting thing that happens here as well. If you have an interface which has a port 80 rule saying you can connect to the web server at con HTTPD, so you successfully connect to it. You have an interface default rule which says the interface default is con default, just like before. Well, somebody coming in and connecting to the web server at con HTTPD, when they break through the CGI program or something, say that PHF is running on there or something really bad is there, and they try and spawn off a shell or create a bind shell or backdoor the system or create some way so that the remote user can connect in, they're not going to be able to do it because the web server can only communicate out one port, port 80, because that's the only rule that it's allowed to communicate on. So now you can actually restrict how processes can communicate over the network. It's not only just saying that somebody can come in and talk, somebody remotely can talk to this one, but you can specifically say this process is allowed to talk out to this host, and this process is not, or this process is not allowed to talk to the public network. For example, your internal database, you probably don't ever want that talking to the internet directly. You're going to want to talk it through some intermediary means. So that's another ramification. One of the things that comes out of all this in trusted operating systems is the idea of a security gateway. And a security gate is a way to take 2 disjoint subsystems and to actually allow some communication between them. So in the previous example, you had a web server that was running, and you had an SQL server that was running, and you couldn't communicate between those 2. But you might want to allow some of the CGI programs to talk to the database. You don't want it to have access to any of the files. You don't want to give it any other kind of access. You just want to have a limited communication path between them. Security gates are what allow you to do that. A security gate is a very small program written by security experts and checked that allows one-to-one network-based communication, and it's a privileged program, and that's what we call a trusted program. Because we've given it special rights, we want to check it and make sure that it actually is going to behave correctly. And this just kind of goes through the example that I showed you before. Here we have CGI program, SQL program that are disjoint, can't communicate with each other. And if we plop a security gate in between them, it will arbitrate access between those two things. And you can do other interesting things as well with security gates if you want to. You could extend that out and actually audit the connections between the two and do look at the data flow. For example, if you wanted to check all of the SQL traffic and see if it's valid, or if you want to do some more security on your SQL server, you could do things like that with a security gate, with that concept. The next thing to briefly mention is the idea of a CGI daemon. This is something else that we do. The idea behind a CGI daemon is that you may want to separate CGI functionality away from the web server. Right now on regular web servers, what happens is that the web server simply runs the CGI programs. It forks and execs them off. And those programs run as the web server user. Well, there's a problem there. If somebody breaks a CGI program, they can send signals to the web server and they can kill it. They own it because it's the same user. With CGID, you're separate. Actually, I should probably go to the slide here. You're actually separating it out, and you can put it entirely in its own environment. And so you can run it in a different SL, you can run it as a different user, you can run it with different rights. And you can decide how you want to encapsulate the CGI programs. And you have a security gate between the two that will allow the communication to take place. All right, so I've talked about a lot of functionality and what kind of all the pieces of trusted operating systems are, but how do they address the kind of the core failures or difficulties with standard platforms? And again, these are things like buffer overflows, misdirecting root programs, the ability to give away any file that you own, and the lack of network access control. Buffer overflow attacks are addressed by least privilege or capabilities. And right away you have a situation now where you can run programs with minimal abilities, minimal capabilities, or privileges. And programs can drop their special abilities whenever they want to without having to become another user. They can just simply say, I don't want these abilities anymore, I don't need them. And they can get rid of them. And there's something else that's interesting that happens here. A web server that's able to bind to port 80 is not as interesting as a web server that has access to every file in the system. A mount command, which allows you to mount a file system, while still a very useful thing to attack on a system, is not the same as buffer overflowing attack. Buffer overflowing that program, getting a root shell that gives you privileged access to the entire system. So you've got a case now where even if you break one of these programs and you happen to get a privilege, you're only going to get access to the specific privilege that program has if it hasn't dropped it. So now your access is still very limited, and you can restrict the damage. To go back kind of to the example here is simply that you have the web server that binds a privileged port, and all it needs is a privilege that allows it to do it. Once it's done that, it can drop it. It doesn't need it anymore, and now there's really not a whole lot of reason to attack this process because it's not going to give you any kind of special access. And again, under standard Unix, the web server, even if it's for a brief amount of time, has access to the entire system. Under a trusted operating system, it doesn't have to be this way. And as I said, least privilege reduces the damage that's caused. And most attacks, at least today, are, if people have looked at them, are the idea of trying to get a shell code or those sorts of things, are attacks based on the idea that once your attack is successful, you'll have unrestricted access to the system. Under a trusted operating system, the same attack will probably not yield the same level of access, if any access at all. Just to give a little example of how you can use least privilege in a programmatic sense. Under standard Unix, you have your program code, big chunk of code. It could be really long, like Netscape Enterprise Server or something like that, or it could be something really small. You have to review all of your code. If it's going to run as root, you need to check every bit of code that's ever going to be run as root, which is probably all of it. And that's a lot of auditing to do on software. And most people don't have the time to do it, and most people aren't qualified to do it either. And every point in the program is a potential vulnerability. If you're using a privileging system, then what you can do is enable the privileges only when you need them and disable them when you don't. Which means now if somebody's trying to misdirect your program, it's only going to be useful if they misdirect it during the time when the privileges are enabled. And buffer overflows will only work if the privileges are still in the maximum set on the process. If the process has dropped them, then the buffer overflow doesn't gain you anything because you've run the program. It's probably running as you, or even if it's running as another user, you're not going to have any special access to the system. You're still going to be locked into your Mac SL compartment. You're not going to be able to escape that, and you're going to be trapped. The old problem on standard Unix is that a user who owns a file can modify it if they want to, can give access away to it. Under Mac, it's different. And here's a simple example of some things that you can do. Most system files on a Unix box are owned by root, which means under standard Unix, root has the ability to modify any of these files anytime at his discretion. Under a mandatory access control system, you can do something very simple. You can place all the system files at implementation low, the lowest SL on the system that's dominated by every other SL, which means every process, no matter what SL it has, can read these files, which means it can use them. It can use the libraries. It can read them so far as the mandatory access control rule goes. It still has to pass the discretionary access control rule. Now, what you can do is you can say that every user who logs into this system, even root, will log in as confidential. So now you have a root user sitting on your system who would normally have DAC access to all these files, who won't have that access anymore. They will only have read access to the files. They'll be able to run programs, but they won't be able to modify any files. So now you have an impotent account on your system. And this is a very classic way of taking a trusted operating system and protecting your system from attack, from remote attacks, or even from local attacks. And to reiterate, under a trusted operating system, root is not a special user. UID 0 is the same as UID 1, UID 1024. They're just UIDs. The only way for a user to be able to have any kind of special access on a system is either to get privileges, and typically privileges are obtained by running administrative programs that have privileges on them. And these programs are protected by Mac. They can be protected by authorizations as well. So on a trusted operating system, programs running as root are no different and no more special than any other program running on the system. Network protection. So now you can see that we can use network rules to force a user to enter to be on a system at a specific level, because we can mark their data, and then we can have Telnet or SSHD or whatever put them on the system at that specific level. I can say if this user comes in over the network, no matter who they are going to log in at this level. They can't even request a different level. They will be at this locked-in compartment. And so now you can apply different rules based on interfaces, based on hosts, ports, and also in VPNs, which would fall under interfaces. So from the example before, it now becomes possible to protect critical files on your system, or in fact every file on your system, from attack, simply by using mandatory access control to protect them. And because a user cannot escape MAC, there's no way for him to circumvent the protection. So to sum up the differences here, we can now run services at different users, or even as root still, because as I said, it's not a special user. We can run these programs with least privilege so that they only have the rights that they need, only when they need them. So now remote attacks are going to be less successful. And set UID programs, which normally were set UID because they need to become root to do what they needed, probably won't be set UID programs anymore. They'll just be run as the user, but they'll only have specific privileges that they need, and they'll do checks to make sure that the user is actually allowed to run them. And then finally, of course, you can decide that a user coming in from one connection will have a different type of access to the system than that very same user coming in from another connection. Even if they have the account, even if they remotely break into the system and SU to that user, you can lock them out from gaining the abilities that that user might have. Now I'm going to go briefly, I guess I kind of flew through this one, through two examples of how you can actually use this stuff. The first is a basic web server, and this is just how can you go about securing a web server? What are the kinds of things you can do with this to protect your web server from attack? And the second one is kind of a fun and games one, and I started to talk about a little bit with root, but it's how can you create a system where root's a guest account? And at this point, I'll actually take a second to mention something. For those of you who are staying on at DEF CON, we actually brought a box in that's going to be used during the DEF CON Capture the Flag competition, which is essentially a hacking competition where one side is hackers and the other side is bastard operators from hell. Well, normally I'd love to play the hacker, but this time I just decided to play the BOFH. And we brought in a box that's protected by Pitbull, and I'll be a little cocky and say I don't think anybody's going to break into it. What we're doing is on the first day we're going to give out this box. We're going to give people accounts onto it and tell them that they can try and break into it. There's going to be web servers, IRC daemons, IMAP POP, SendMail, all kinds of things that people should be able to break into running on it. And on the second day, we're going to give out the SE shadow file. We're going to say, here is the encrypted passwords for all the users on the file. Go run crack on it, get the passwords, because they're going to be really simple. And if anybody doesn't get them, then they should probably join a different team. They'll have the administrator account, they'll have the root account, they'll have all these things, and yet they're not going to be able to have any kind of access to the system except for this little environment that we're going to allow them to play in. And that's to kind of drive home the first piece is see how you're isolated, see how you can't do anything to the system. And then the second is to drill in the idea that user accounts don't matter as much anymore, that we can really play around with them and decide when and where users can do what we want them to do. So, for these two examples, I just wanted to mention the labels I'm going to use. They're top secret, confidential, unclassified, implementation low with kind of the standard arrangement. And then compartments, I'm going to use web, mail, and the ever creative A compartment. For a web server, this is kind of a diagram here, and what I've shown is the lines actually show communication paths. Ideas of someone will come in over a network and connect to a file transfer subsystem, which would be SSH and FTP. They would come in and connect to a web server, and that's essentially the two things that we have in this example. And the first thing we want to do is let's take a look at the files and protect these files from attack. So we have, as far as the web server goes, we have two types of files. We have web content, the CGI and the HTML, and then we have web server files, the binary files, the actual web server binary. Someone comes in and modifies that, reboots the system, well then you have a web server running, a little bit differently. And then it's configuration files. In this case, I would want to protect the content at unclassified web. And I would want to protect the configuration files at unclassified web conf. And that I just gave them names that would kind of make a little bit of sense. If I wanted to, I could put the configuration files at the same level as the content and say, I'm going to let a web admin come in through the file transfer subsystem and be able to modify those files. And if you look at the rule, how it's set up is that FTP and SSH come in at unclassified web, which means if a user comes in through those services and authenticates themselves, they'll be able to modify the content because they'll be at the same level, right? So clearly using SSH in this example is probably better than using FTP, which is no different than standard Unix because someone might sniff the password. And in fact, we could restrict these rules even more and say this user has to come in to modify the content from a specific host or from a specific interface. The next thing we want to protect is, of course, the system configuration files. Things like etc shadow, etc password, all of the libraries, logs, networking, configuration files, all those kinds of things. Put those all at implementation low, because those are all things that we're going to want people to be able to read, but not be able to write to. And the other things that we want to protect differently, like, for example, etc shadow, we'll protect using discretionary access control, because the two access control mechanisms can complement each other. Now, the important thing, the web server is going to run at conweb And what this means is that it dominates the labels of both the content and the server files. So now you have a web server which is running that has read access to its content, but not write access. And if someone comes in and breaks into CGI programs or whatever gets in there, they're going to be at that level. And there isn't a way for them to break out of that level and gain write access to those files. No matter what user they become, no matter what they do on the system, they're trapped. So now you have a case where very simply you've architected a web server that even if it's hacked, can't have its content modified. So if you have a really bad Perl programmers or whatever employed by you, granted, you want to teach them how to program, but you're a lot safer with this kind of system. And I kind of already briefly went over the network interface here. I guess the last thing again is to say that on port 80, I say you come in at a specific level which allows you to connect to the web server, and that's just a reiteration of some of the things I talked about previously. So root is a guest account. This is going to be just a block diagram, mostly because I started to think I had way too many slides, so I wanted to make it a little bit simpler. I'm dealing with three subsystems on here. One is system files, which, like before, I'll protect at implementation low. It's a fairly standard thing to do. The next is that if a connection comes in over Telnet D through this interface, through port 23, I'm going to put it at confidential user, which means anybody who comes in over this connection will be at an SL of confidential user, which means they'll have read-only access to the system files, so they'll be able to run programs and do the things that they want to do, but they won't be able to write to them. So even if you come in and you give away root, the root account, you post, root password, blah, 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 1, or whatever you want to do, they'll have a root shell in the system, but it won't buy them anything. And if they haven't encountered this before, I'm sure they'll be really puzzled to try and figure out why they're not able to mess up the system. In a little while, they'll figure out why. The other part in here is that on the same server, I set up a situation where I wanted to have a mail subsystem. I want to pop IMAP send mail, and then all the mail files associated with that. Well, I'm going to run all of those in its files at confidential mail. And then I'm going to make network rules that allow people to connect to them and use them. Now, if somebody comes in and breaks into this mail subsystem, they're not going to be able to go over and go after any of the user subsystems. They won't be able to go after their files. And likewise, anybody who breaks into the user subsystem or who comes in there will not be able to access the mail subsystem on that same machine. Now, they will be able to go across the network and access it like any other user was able to, because we've set up the rules so that they can do that. But there's no cross-file access, and there's no way for a user to break out of their compartmentalization to try and modify those things. I should mention, as far as commercial trusted operating system platforms, right now there are really two vendors who are creating commercial versions of trusted operating systems. One, of course, is the company that I work for, Argus Systems Group, a really great company. We do a Solaris 7 Spark and x86 version of Pitbull. We're porting to Solaris 8. We're backporting to Solaris 6. We have an early access version available on AIX, and we're porting to Linux on 32-bit and 64-bit kernels. HP also has a product available called Virtual Vault. Virtual Vault is available through the Presidium suite, I guess is the right way to say that, and that runs on HP hardware. The other thing to mention is that we have a program going called the Argus Revolution, and we actually gave away all of our CDs today, but we'll have more tomorrow during lunch, where we're giving away Pitbull for free, the trusted operating system, for individual non-commercial use. So anybody who's got cable modems at home and wants to set up proxies or gateways or whatever to keep their home from being hacked and turned into a porn site or where site or whatever, this is a great way to do it. And on the Argus Revolution site, we're starting to talk about how, the kinds of things that you can do to protect your systems from attack. And of course, we sell our product commercially too. That's all. Happy to take any questions if anybody has any, or thoughts or anything along those lines. Yes?
You build a trusted operating system, you run HTTP there. Is there any hacking you have to do with the web names? How does it affect the names?
All right. The question is, if you run like, for example, a web server on a trusted operating system, does it affect the web server in any way? Is there anything special that you might have to do to the web server in order to get it to run on there? That's one of the reasons why I said commercial trusted operating systems. And even with Virtual Vault, that's not entirely true, so maybe I should just say for myself. No, you really don't. You don't need, certainly from a code perspective, you do not need to modify it at all, particularly if the vendor maintains the platform API, which we do, so it will be completely backwards compatible. Typically, all you're doing is extending the security APIs on the system. Now, one of the things that you would have to do in that situation is that HTTP uses a privilege. It needs to bind to a privilege port. So you need to put a privilege on the program. And for example, with Pitbull, we provide a program called TracePV, which automates that whole process. It can go through and look at a binary and determine what privileges it needs to run and put all that stuff into place. Now, of course, you can go back and take the code like the Apache web server and modify it to be even more intelligent to raise its privileges at the right point, drop them at the right point, and do those sorts of things. So you can actually start to do a little more secure development if you want to, but you don't have to. Any other questions? Yep.
You basically add the second layer of privileges all the way around as an additional term with the basic operating system, like this thing you're going to be giving away. The person installing that is not probably going to have a trusted systems background.
Yes.
Is it locked out of the box or open out of the box?
Oh, our stuff is pretty much locked out of the box. And so yes, if somebody installs
While you're learning about it, you're not involved.
Yes. Right. No, it's not where you can become root and everything. There are things that you can do to the box to make it increasingly secure, but a lot of those things deal more with how you want to set up your architecture than they do with this is vulnerable and this is not vulnerable. Yes.
What do you do, like, all this, how do you set a machine up and set up basically as installing
All right, so your question is one is kind of like how does the install go and how do you integrate once you have it installed? Right, okay. The first thing is that, at least with our product, it installs on top of the operating system. So it's not like a fresh install. You don't have to start over. If you have an existing system, you can install this on top of it. Right, that's the first piece. The second part is if you have applications that are running on there, and I kind of mentioned this with the Apache server, that essentially what you're going to look at is you're going to say there are certain daemons which are running on my system which need to ran as root at some point before. The reason why they ran it as root was because they needed some sort of special access to the system. Those are the programs that you're going to have to go and take a look at and run this trace PV program that I mentioned before. And I keep pointing at him because he was one of the guys involved in writing it, so it's kind of habit. You run that, and that will actually set up the applications to run with the correct privileges. So those are kind of the two pieces. Applications that don't need special access to the system, that don't need those sorts of things, there's no integration at all. They just work because they're not doing anything security relevant. Yes?
How do you handle backups and restores without approved root?
Right, okay. That's the one subsystem I'm least familiar with. So, do you want to? I'm sorry? Oh, well, okay. That's part of it. One of the things there's two ways you can do it. I'll just kind of explain a little bit. One, like we modify backup and restore under standard Solaris, and it understands the security parameters that we put on the files, the extra security objects, and what those programs will have privileges on them which allow them access to the file system so that they can obtain all the files and do what they normally do. The difference is what you do is on those programs you'll put an authorization on them, and you'll say the only person who can run these is the backup administrator, if you only wanted to say there's a backup administrator, right? And then what you can do then is place a user in to have that authorization. You say this user is a backup administrator, and they'll be able to run those programs. There's another thing I should mention, is now what you can do beyond that, beyond just saying simply that this user can do this, because now you're in the case where, well, okay, that user connecting from AOL can do it too. Well, now what you can do is you can take these administrative programs and you can protect them with MAC as well. So now you can say you have to be a user with this authorization, you have to be able to run these programs, and you have to come in from the right place to be able to do it. So you can apply all those levels to that in order to allow somebody to back up or to not allow them to back up the system. Does that answer your question reasonably well?
Yeah, I think there's a few problems with that.
Okay, well, we can talk about it a little bit more. Yes?
The same basic backup restores throw patches and OS upgrades to keep lockouts whenever everybody. For example, your DEFCON example.
Yes.
When you lock out so that no user can do anything to go out of the file, what do you need to add your files and patch and upgrade them?
If you need to do those sorts of things.
Right.
Yes, okay.
So what are something has that?
Yes, you can, but again, you can do several things. One is you can say either they have to come from console or they have to come from a specific interface, from a specific host. You can decide who it is and where it is that they have to come from in order to do that. Or you can put the system into a special mode where you can lock out remote access and say now we can perform these operations. And that's a concept that we put in called operational mode or maintenance mode. And maintenance mode is the situation where you would do those sorts of things if you wanted to use those mechanisms. Yes?
Do you have like numbers, for example, what kind of performance that you take for running just always enough for this number?
Yeah, sure. This is the guy who actually did a lot of our performance tests. What was it?
It's like 5-7%.
5 or 7%. So it's pretty minimal. Yes?
How do you reduce the backup file? Like if I have a user that's logged in at a confidential level, when they produce a file, by default, the files require confidential access.
Yes.
What if they want to go and reduce it to unclassified, but unweb?
Right. Okay, the short answer is they can't. And the long answer is that one is that if you created you would have accounts in your system which are called well, there's several things you could do. You could have an account in a system which would be a security officer who could modify it. The other thing you could do, and a customer we have has done this, is that you can create kind of a gateway program that would allow them to modify the labels on those files if you wanted. And that's the idea where you're saying, for example, I don't really trust this user to write everything correctly. I want to review their code. So they might write it in one compartment. Well, then they may need to transfer it over intermediately to another place where it's protected, and that's where the reviewers might look at it, and then it would go onto the system. So you can do those kinds of things. The answer to anytime you want to ask the question of how do I circumvent the security on the system, and that's that kind of question. And there are always good reasons why you might want to do it, but you obviously have to think about them a little bit. The answer is always you need a privilege to do it, and then which probably means you have a program that performs that operation, and then obviously you can use authorizations and mandatory access control to protect those programs and to decide who and when and how they can use those. Any other questions? Yeah, another one. All right.
Do you support IPSO Basic or SIPSO?
Yes, that's what I was talking before. We support IPSO, RIPSO, and we also have, I don't know if you're familiar with SAMP RE, T6 stuff. We have kind of a homegrown version of that as well. And that's just to transfer every piece of security information. But we support all of those as well. The question that he asked before was whether or not we support IPSO or SIPSO network labeling, and that was referring, as I said, that was referring before to my comments on being able to transfer labels across the network. Those are actually the protocols that allow you to do that, and they embed themselves in, at least RIPSO and SIPSO embed themselves in the IP option layer, and that's where you would put that payload. Any other questions I can answer? Right, if you guys think of anything else, we'll be around at our booth out there somewhere. And as I said, we will have CDs and literature, and I believe T-shirts again available tomorrow. I'm sorry? Yeah, you can get all of the CDs. The products are available on the website, and we'll have the x86 CDs here tomorrow as well. And then you can get support and things like that through the site too. Yes, we do. They will be available